a lithography tool that took Dutch engineers and roughly 400 corporate partners multiple decades to bring to commercial production. China's domestic version of the generation below, it crossed a production threshold in what independent analysts estimate as under 3 years of serious state-directed effort. That is not a typo, and it is not a press release. It is the rate that makes this race worth clocking. The question is not whether ASML still leads. It does by a distance that would embarrass most sprint timers. The question is whether the gap between tool generations is shrinking faster than ASML can extend the finish line. And that question has a measurably different answer today than it had 18 months ago. Start with one machine. Not the frontier tool, not the one whose acronym fills every semiconductor headline, but the workhorse, the dry, deep ultraviolet stepper that prints the geometries inside most of the chips running your devices right now. Follow this class of machine, its optics, its light source, its overlay precision, generation by generation, and you have the whole race. Everything else is commentary on where that machine is headed. A lithography race is not scored by who owns the most advanced machine at any single moment. It is scored by how many years separate each side at each generation rung, and whether that year count is falling or holding. What China has begun doing is not catching ASML. It is compressing the per-generation lag at the lower rungs. And compression at the lower rungs is precisely what funds the climb to the harder ones. The dry, deep ultraviolet stepper is where China's domestic lithography story actually begins. Not in a press release, but in a fab qualification report. ASML's dry, deep ultraviolet line, the PAS and early twin-scan generations, reached production maturity across the 1990s and early 2000s. These are not frontier machines. ASML still ships them for trailing-edge work. The manufacturing knowledge embedded in their alignment systems, light sources, and vibration isolation is decades old and distributed across a supply chain that spans the Netherlands, Germany, Japan, and the United States. Every component in that chain has been iterated through hundreds of production generations. The tool you buy today carries the compounded engineering of roughly 30 years of real fab feedback. Shanghai Microelectronics Equipment, the company the Chinese state designated as domestic lithography champion in the mid-2000s, spent most of the following decade qualifying tools for packaging and back-end work, rather than front-end wafer printing at competitive geometries. That distinction matters. Printing the outer layers of a finished chip is a fundamentally less demanding task than printing the transistor layer of a logic die. For a long time, the gap between those two tasks was the gap between SMEE and ASML. Reports from Chinese state media and semiconductor industry observers suggest that gap began closing in the last few years. SMEE's own claims put their most advanced dry, deep ultraviolet tool at 90 nanometer capability, geometries relevant to mature node logic production. No independent benchmark from a leading commercial fab has publicly confirmed yield at that node. And here is where I want to flag something directly. Delivery is not yield. A tool that ships is not the same as a tool that prints acceptable wafers at production rates. Early reports from Chinese fabs using domestic steppers describe overlay error and uptime figures that would be rejected at any leading-edge facility. The clock is running on SMEE's delivery claim. Whether the split narrows further depends on yield data that has not yet emerged publicly. Think of it as a distance runner who spent 15 years in the training oval finally entering a sanctioned race. The leaders finished long ago. The question is not where the leaders are. It is whether this runner's lap times are falling and whether the remaining track gets longer or shorter. ASML's dry, deep ultraviolet production clock, mature by the early 2000s after a multi-decade development runway. SMEE's domestic equivalent, arriving at a production-adjacent threshold now, trailing by what analysts loosely estimate as 15 to 20 years in tool generation terms, but with the last 5 years compressing faster than the prior 15. Gap this leg, wide, and the per-year closure rate is the number worth watching. That closure rate makes the next leg harder to read honestly, because the immersion deep ultraviolet rung, the same class of machine, but with water added between lens and wafer, is where the gap suddenly widens again. ASML's twin-scan, XT and NXT families work by flooding the gap between lens and wafer with ultrapure water, which has a higher refractive index than air and lets the same light source print at finer geometries than the physics of dry exposure would otherwise permit. The engineering challenge is not exotic in concept. It is contamination control, fluid dynamics at nanometer tolerances, and overlay precision maintained across thousands of wafers running at production speed. ASML, in partnership with lens supplier Zeiss and a constellation of process chemistry firms, commercialized this in the mid-2000s. Immersion deep ultraviolet tools remain the workhorse of the global leading-edge fab world for nodes down to what multi-patterning can reach. Adding water sounds trivial. It is not. Maintaining a stable fluid film at nanometer tolerances across a wafer moving at production speed, while holding overlay error below the width of a few dozen atoms, is closer to holding a soap bubble flat while running than to hosing down a surface. Every component in the system has to be re-engineered around that fluid. SMEE has publicly targeted immersion deep ultraviolet capability. As of the most recent publicly available information, the company has not shipped a production-qualified immersion tool to a front-end fab. The immersion step requires a different grade of optical system. Zeiss, the primary supplier of ASML's lens assemblies, operates under export control constraints that limit what it can ship to China. Domestic Chinese optics firms have state backing to develop alternatives, but the precision tolerances involved, lens flatness measured in fractions of a nanometer across the full aperture, represent a different class of manufacturing challenge than the dry deep ultraviolet system. Research institutions in China are working on immersion-capable systems. No production deployment has been publicly confirmed. ASML's immersion deep ultraviolet tools, in volume production at leading fabs since the mid-2000s, roughly 2 decades of deployment maturity at the time of this script. China's domestic immersion deep ultraviolet, no confirmed production tool in available reporting. Gap this leg. The year count widens relative to the dry rung. Where the dry gap was roughly 15 to 20 years, the immersion gap, measured by production deployment, is at minimum that, and the clock on China's side has not started in any confirmed sense. Here is the part of this race that almost every piece of coverage skips, and it is the most underreported dimension of the contest. Before extreme ultraviolet lithography arrived in volume production, TSMC, Samsung, and Intel all used multi-patterning to push deep ultraviolet tools below the geometries those tools were nominally designed for. The technique, expose, etch, align, repeat, sometimes 4 times on the same layer, is computationally intensive, yield-sensitive, and expensive in cycle time. It is also undeniably real. It is how chips at 10 nanometer and 7 nanometer class nodes were printed without extreme ultraviolet. ASML's tools were the platform. The process innovation was in how fabs used them. Most coverage jumps straight from China cannot get extreme ultraviolet to China is stuck. That framing skips the workaround that the global industry itself used for years, and it understates what China is now demonstrating. Multi-patterning is the chip equivalent of running the same relay leg 4 times before handing the baton. You cover the distance, the clock cost is real, and you cannot keep doing it indefinitely as the baton gets lighter and the legs get shorter. But you can absolutely run that relay, and if you run it well, you cross nodes that looked out of reach on a single exposure. A single exposure on a deep ultraviolet immersion tool resolves features at roughly 38 nanometers half pitch before multi-patterning. To reach the geometries needed for leading-edge logic, fabs stack 4 or more of those exposures with overlay alignment tighter than 3 nanometers. About 1/30th the width of a strand of deoxyribonucleic acid. Every alignment error in that stack compounds. The tolerance is not a margin, it is the product. China's most advanced domestic fabs, SMIC foremost among them, have demonstrated multi-patterning capability. The chip produced by SMIC for Huawei's Mate 60 Pro, identified by TechInsight's teardown analysis, appears to use a multi-patterning deep ultraviolet process rather than extreme ultraviolet. This is not a performance equivalent of a TSMC 7 nanometer extreme ultraviolet chip. The density, power envelope, and yield economics differ. But it demonstrates that multi-patterning on available deep ultraviolet tools is not theoretical. It is running in a Chinese fab, on Chinese-assembled equipment lineups, producing parts that ship in consumer devices. ASML enabled multi-patterning at the frontier, mature and largely superseded by extreme ultraviolet. TSMC moved its leading edge to extreme ultraviolet years ago. China's multi-patterning on available deep ultraviolet, arriving now at nodes the Western ecosystem passed several years ago, but with evidence of production-grade execution. Gap this leg, measured not in tool generation, but in process maturity. ASML's customers are roughly one full node generation ahead at the multi-patterning tier, but China is on the track. This is the leg where the gap compresses most in pure rate of closure terms. Now comes the part of this race where I am going to slow the rhythm down, because the honest read of this contest requires it. Extreme ultraviolet lithography is where China is not yet on the track. And I want to be precise about what that means, because it is different in kind from being behind on the previous rungs. ASML's extreme ultraviolet monopoly is structural, not accidental. The light source, a tin droplet struck by a laser 50,000 times per second, generating plasma that emits light at 13.5 nanometer wavelength, took decades of co-development between ASML, Cymer, now an ASML subsidiary, and a network of national labs and optics firms to stabilize at production power levels. The reflective optics, extreme ultraviolet light, cannot pass through glass, so every mirror in the system is a precision multi-layer coating. Come from Zeiss under a partnership so deep that ASML holds an equity stake in the relevant Zeiss division. No other company on Earth ships a production extreme ultraviolet tool. TSMC, Samsung, and Intel have collectively placed orders running into the hundreds of machines. Each machine costs in the range of hundreds of millions of dollars and takes years to install and qualify. China does not have a domestic extreme ultraviolet tool. This is not a gap that is quietly closing in a lab somewhere and about to surface. Chinese research institutions have published work on extreme ultraviolet relevant optics and light sources. Research publication and production tool readiness are separated by a gulf that took ASML itself the better part of 2 decades to cross, and ASML crossed it with access to the global supply chain that China currently cannot fully access. Export controls block extreme ultraviolet tool shipment to China. They also increasingly constrain specific components, certain lens assemblies, vacuum system parts, photoresist chemistries sensitive to extreme ultraviolet wavelength that a domestic program would need to source. The strongest case that China's extreme ultraviolet gap is a mirage. State investment is large, sustained, and directed specifically at this choke point. The government has publicly identified lithography as the critical constraint. Funding is not the binding limit. If China were to achieve even a modest power extreme ultraviolet source with production-adequate mirror lifetime, the strategic narrative would shift quickly. And the announced ambition is exactly that. The strongest case that the lead is real. It is not the machine alone. It is the ecosystem that makes the machine reliable enough to run at production. Extreme ultraviolet tools at TSMC achieve uptime and wafer output figures that took years of iterative engineering between ASML, the fab, and dozens of subsystem suppliers to reach. Even if China fields a domestic extreme ultraviolet prototype, the distance between prototype and production qualified tool, measured in wafer starts per hour, availability percentage, and overlay control across a full production run, is where the gap is most durable. Prototypes do not print chips at volume. Production qualified tools do. My read. The extreme ultraviolet gap is real and structural, not because China lacks ambition or capital, but because the system-level co-evolution between tool maker, optics supplier, light source chemistry, and fab process is not something any single funded program replicates quickly. The light source alone required roughly 15 years of co-development between ASML and Cymer to stabilize at production power. The multi-layer mirror flatness tolerances, surface variation below 1/10 of a nanometer across the full aperture, are documented in open literature. Production-grade execution at extreme ultraviolet wavelength has not been publicly demonstrated by any Chinese optics firm. I do not think China fields a production-ready domestic extreme ultraviolet tool in the next 5 years. I hold that view, even while calling the deep ultraviolet compression story entirely real. Both things are true simultaneously, and neither cancels the other. Imagine a climber who has just topped the 3rd pitch of a 5-pitch route. The split times on the lower pitches are genuinely compressing. The 5th pitch is a different rock type, overhanging, no existing protection, and the gap to the leader on pitch 5 is not a speed problem. It is a route-finding problem no one at base camp has solved yet. ASML, extreme ultraviolet, in volume production at leading fabs since roughly 2019 and 2020, with output scaling each year since. China domestic extreme ultraviolet, no production tool, no confirmed production-ready prototype. Timeline to first production deployment unmeasured because the clock has not started in any publicly verifiable sense. Gap this leg. Not a year count. It is an existence gap. China is not yet on this leg of the race. 50,000 tin droplets per second, each struck by a precision laser pulse, each generating a plasma burst lasting nanoseconds that must hit the same target aperture every time. Miss the alignment fractionally, and light output drops. Miss it consistently, and the mirrors coat with tin and go dark. Keeping that system at production uptime is less like running a machine and more like conducting an orchestra where every instrument is also a small controlled explosion. That is not a problem that yields to funding on a short timeline. It yields to iteration, and iteration requires a working system to iterate on. 12 months from now, SMEE ships more dry, deep ultraviolet tools into Chinese fabs. Domestic immersion, deep ultraviolet remains in development, with no confirmed production deployment. Multi-patterning at SMIC continues to push mature node output. The extreme ultraviolet gap is unchanged in structural terms, though Chinese research publications on light sources and optics will accumulate. The tool generation scoreboard at that point, China closes slightly on deep ultraviolet rung 1, holds distance on deep ultraviolet rung 2, demonstrates production-grade multi-patterning more broadly, does not field domestic extreme ultraviolet. My call on the larger question: the race is real and the compression on the lower rungs is real, but the extreme ultraviolet rung is not one China reaches in this decade under current trajectory. What China is building is a parallel track, mature node domestic capability at scale, and that track has economic and strategic value independent of whether it ever reaches the extreme ultraviolet tier. The question worth sitting with is whether parallel track at mature nodes constitutes catching ASML or constitutes building a different race entirely. I think it is the latter, and I think that distinction matters more than most analysts currently price in. That dry, deep ultraviolet stepper we started with, the workhorse, the one tool class SMEE has come closest to domesticating, is now in Chinese fabs running Chinese wafers, closing a gap that was not closing 5 years ago. It does not threaten ASML's frontier position, but it is the first rung that any longer climb requires. Without it, nothing above it is reachable. With it, the next question is already forming. The story was never about who owns the most advanced machine. It was about which side's clock is accelerating, and on the rungs China can reach, that clock is moving. The ceiling is real. The floor is no longer fixed. ASML has not lost a step, but the distance between steps is not what it was. Here is the question I want you to sit with. If China achieves production-grade immersion, deep ultraviolet capability in the next 3 years, does multi-patterning on domestic tools get close enough to 7 nanometer class geometries that the extreme ultraviolet gap becomes strategically irrelevant for the markets China actually needs to serve? And what does ASML do when the answer to that might be yes? Leave your read in the comments. And if this is the kind of race you want to keep clocking, subscribe and turn on notifications, because the next split is already closing.